One of the things we need to think about for waves is the idea of superposition, which is simply a fancy word for adding them together. And the reason we need to add them together is that waves can pass through one another. If we imagine two balls being shot such that there's a spot where they would be in the same place at the same time, we know that they collide and bounce off. So we know for physical objects that two physical objects cannot occupy the same location at the same moment of time. Right? If I throw a ball at a wall, it bounces back. It doesn't go through the wall. Sound, on the other hand, is very different. Sound can pass through. So if we imagine two speakers, the sound from one and the sound from the other just pass through. There's no bouncing off that really happens here. Now, we would say that in a way the waves interact, and that's what we're going to call superposition, but it's simply that they're both here. Passing through one another doesn't actually change the wave as it continues on. So this is a pretty important idea. We're going to talk a little bit through what this means. I'll show you one example here, and then this is actually one of the ways that we get to standing waves. So this has a few different values to it. So to think about superposition, we're going to start by thinking about traveling waves. So we're going to take two traveling waves that for simplicity are traveling towards each other at the same speed in opposite directions, as you can see. Now in this case, we're going to look at two pulses that have different shapes, and this is just to kind of think through how they're being added together. So a nice simple cartoon. So at time t equals 0, these pulses are at different places. We can think of these as pulses on a string, for instance, but they have a velocity. They're moving towards one another. So sometime later, this 1 second later, the center of this pulse, instead of being at 1 meter, it's now at 2 meters. The center of this pulse, instead of being at 5, it's at 4. So this is exactly what you would expect. But note, after this, they're actually going to be overlapping a little bit. So we now have to ask what is actually going to happen. So a little bit later, they are now in the same place. So what we've done here is this one is there basically, and we are then putting this one on top of it. So that is basically just adding another one, but you wouldn't just say, oh, they're the same, so they're both there. What you actually get is then the sum. This triangle-y bit is twice what it was originally because these are identical. Now, this part of the wave, nothing happens because no part of this is over there. So hopefully that makes a little bit of sense. We can think what's going to happen a little bit later then. So now, as this part continues to move, this is now over top of this. And you can see that they're basically opposites, despite my bad drawing. So we call this destructive interference. When you sum two opposites together, you get 0. And so the dashed lines are showing the original wave, and then there's just a straight blue line here. There's seemingly nothing there. But this first part of the wave that was originally on the right has now just passed through. So this is what's over there. So even though before this was interacting with that wave, it's now unchanged. These are destructively interfering, and that's like the idea of adding a positive number to a negative number. You get 0. So a little bit later, what happens? They are now unchanged. And what's helpful to note here is that there's actually a breaking point. So this is this wave, and this is that wave. So even though there was previously destructive interference that made the string go to 0, it doesn't stay 0. We see this reappear. So this is a really important idea, that when you have superposition, you then keep thinking about each component of your wave. If your wave momentarily has destructive interference, or perfectly destructive interference, it doesn't stay gone. So that's the idea of superposition. Hopefully that makes sense. Again, all we're doing is really just adding every single point on the wave together. So why do we care? I want to show you one example that's really important, and the book doesn't really go into this. And this is the idea of complex sounds. So when we're talking about sound waves, we're going to keep talking about simple sinusoidal sounds, but that's not actually what sounds sound like. So a very boring sine wave doesn't sound very pleasant to your ear. If we were to actually look at the sound wave coming from a flute or a violin or a guitar or whatever your favorite instrument is, or even the human voice, it looks much more complicated. Using the idea of superposition, we can see why it is helpful to talk about sinusoidal waves at all. So let's start by thinking about a simple sine wave. Now, I'm not going to be really considering differences in amplitudes as I show you this. I'm just going to be thinking about differences in wavelength or time. So you can think of this either as a plot of a history plot that shows a different time, or you can think of this as a snapshot graph that is showing you different wave locations at one moment in time. So again, this idea actually doesn't matter whether we're talking about it in terms of a wavelength or frequency. So we're going to start with this, and we're going to add another wave to it. So the red one is showing what I'm adding to the first one, and the next line shows the sum. So we're using superposition to get there. So hopefully this is clear to you, and one of the ways that you can kind of see what's going on is to pick a few points. And you want to pick a point, for instance here, both of them are 0, and if you add 0 together, you get 0. If we now look at a different point, like here, notice that we have a positive value here and a negative value there that are equal in magnitude. Again, going from one of these, like this is 1, this now might actually be 2, that they don't share y-axes. But when you add this together, you also get 0. We can pick a different point, like down here, we see that they're both negative, so we get negative. So if you look at individual points, you can get all of these values. But now notice that when you just simply look at this, you see the fairly fast oscillation present, but you also kind of see an up and down behavior that is matching the other wave. So you can kind of see this by eye. So now let's add another wave to this. Again, I'm going to show it in red here, and then we're looking down here. So now notice that this is already looking more complex. So when I again look at an individual point, again noticing that again my y-axis here does not necessarily match my y-axis here, I'm being very qualitative. I can again pick a point like here where both of my waves were 0, and when I drop this down, I again get 0. I can pick a value, let's see, what's another good one? This one's also 0. I see that I have 0 there. But when I pick a value like here, one of them was 0, one of them wasn't, and again I get a negative value. So again, you can go through, you see 2 negative values, gives you a slightly more negative value, and so on. 2 very positive values gives you a very positive value. So we can again add another component to this that's a sine wave in itself, but that has a different wavelength. So this one's now a shorter wavelength than what we've been adding so far, but notice that it also has a slightly different amplitude. We are adding, in this case, equal amplitudes together, but again, the overall Y scale is a little bit different. So now, look at how messy some of this is. Again, here, my amplitude overall is really small. The wave doesn't get very far away from 0. Here, the amplitude is much bigger. And again, if you pick any point up here, you can add these together and you get those, but you would have to do it for every single point. We can add, now this one actually has a really long wavelength. And again, that's going to make a small change, but since this one has a long wavelength, it's actually a little harder to see its effect. So now when you look at this, this does not look like a sine wave at all. But all we've done is actually sum up a bunch of different sine waves that have different values of wavelength if you want. So the point being that we can make a really complicated looking wave by summing up a bunch of sound waves. And we aren't going to go into it in this class. However, This is the idea of doing a Fourier transform, and you is basically saying, well, what if I want to start with my complex wave and go backwards into its sinusoidal components? And again, if you do analysis of what sounds are actually produced by musical instruments, they look really complicated, but they're actually just coming from summing up a bunch of sine waves.